Hi, in this lecture we will talk about how the LightAutoML works with images and textual data. Let's first think about what we can do with data of this format using existing tools. We already have an implemented tabular AutoML module that performs very well, so we want to reuse it. In order to do this, we need to translate images and text into tabular format. Images can be flattened into a vector or processed with an arbitrary convolutional neural network to extract features. The text can be presented as block of words or TF-IDF, but there are also some methods that are implemented in LightAutoML. All of them share the principle of extracting vector representations from data and passing them to tabular AutoML. Let's start with images. We extract two types of features for each image. First is color histograms. This feature can be very useful for simple tasks when color plays a key role. Second is a vector representation, extracted from an image using a trained convolutional neural network, specifically EfficientNet. We can choose which version of EfficientNet to apply and also whether to focus more on the shape of an object or on their color and texture. After that, we can concatenate color histograms and vector representations in one vector, and if there are any other features in the dataset, we attach them also. Then we pass the resulting vector to tabular AutoML. As we will see in practice part, this simple yet effective image processing approach allows us to achieve pretty good results with almost no effort. Let's move to text. Regardless of the setting, the first approach is to build a TF-IDF representation of the corpus. Optionally, we can apply SVD decomposition to it to reduce the length of the vectors. This approach sometimes works better than deep learning models and doesn't require a lot of computational resources. Also, it can be applied to arbitrary sequences, not just texts. The second feature extraction method is word embeddings. LightAutoML offers three ways to obtain them. We can train the fast text model on our corpus, take embeddings from GloVe or Word2Vec using Gensim library, or provide custom embeddings, which are passed to the model in the form of a dictionary, where each word corresponds to an embedding. Unfortunately, we can't pass raw embeddings to tabular AutoML. We need first to convert them into a vector of a certain length, or in other words, aggregate. There are four methods for this to choose from. Let's take a look at each of them in the details. WAT, or weighted average transformer, is the easiest one. All it does is add up all the embeddings, multiplying them by certain coefficients. Although simple, this approach is the fastest and requires almost no resources. BOREP, or back of random embedding projections, builds on a very interesting discovery. If we take a random matrix and multiply it by each embedding, we will get random projections. By aggregating the projections using any method, for example, taking the maximum values or averaging them, we'll get a vector that stores a lot of information about the original embeddings. We will use these vectors to represent the text. This approach doesn't require any training and is stronger than WAT. But computations are more complex, so it's worth using a GPU. Random LSTM is very similar to BOREP. The only difference is that instead of random matrix, we take a random initialization of the bidirectional LSTM. The output vector is obtained by aggregating the outputs of each cell of this LSTM. Due to its architecture, this approach operates better with sequences of words, although the quality is sometimes worse than that of BOREP. These calculations turn out to be even more complex, so a GPU is also required. Let's move on to the last method based on embeddings, BERT pooling. In terms of working with natural language, everything is standard here. We take a trained BERT, get the context embeddings of each word from the output of the last layer, and aggregate the embeddings. Usually, the embedding of the zero position token is taken. It is also called a classification token. BERT pooling works best in terms of quality, but it's also the most computationally expensive method. In order to get the best quality, we can also fine-tune an arbitrary model from the Hugging Face library. When training, we concatenate text representations from a model with other features and pass the resulting vector to tabular AutoML. This way, the language model trains as an additional ML algo block along with other ones from the preset. It's important to mention that it is the only method that is not available without GPU due to the complexity of the calculations. This is all about methods for natural language processing, but LAMA additionally provides the ability to interpret the resulting text models. The first approach is called LAMA, and it allows you to evaluate the importance of each word from a particular text. It works as follows. We select the text of interest, copy it several times, deleting random words in each copy. Then, in place of each word, we put 1 if it's present in the copy and 0 if it's removed. After that, we calculate model predictions for each copy of the original text. We get a sample in which objects are vectors of zeros and ones and targets are model's predictions. We train lasso on this task and discard features with 0 weights. After that, we train reach on the remaining features. This way, we get a model that sets weights for each word. Those exact weights show word significance. The second interpretation method is called L2X, or Learn to Explain. It trains the model on the entire sample at once and allows you to highlight the most important words in each text. It works as follows. The input is a text presented in the form of arbitrary embeddings. When training, we pass the text to the model, which predicts the importance of tokens, assigning a probability to each token. Then we sample the most important words according to these probabilities and pass these words to another model, which learns to restore the predictions of the original model from them. Both models train simultaneously. Intuitively, the first model should assign higher probability to words that describe the target variable better, because in that case, the second model will produce more accurate predictions. On inference, we discard the second model and leave only the one that predicts the importance of words. During the practice part, we'll see how to use LAMA to solve CV and NLP problems, and also we'll test the performance of both interpretation methods applied to the resulting language model.